All right, so get ready because we're about to take a deep dive into how materials behave electrically.
Yeah.
I mean, it's amazing to me that something like how electrons move can explain everything from why we use copper wires in our homes to how our smartphones store data.
Oh, absolutely. And, you're already familiar with some of the basics.
Oh, yeah.
Yeah, think about how water flows through a pipe.
Okay.
A wider pipe means less resistance and more flow, right?
Right.
Electricity works in a similar way.
So a material that's good at conducting electricity is like a wide pipe for electrons to flow through.
Exactly.
And I'm guessing insulators like the rubber coating around a wire are more like a clogged pipe.
Exactly. We measure how easily electrons flow through a material using something called conductivity.
Oh,
High conductivity means easy flow, like in metals, while low conductivity means the electrons struggle to get through, like in insulators.
so that's the difference between conductors and insulators.
Yeah.
But where do semiconductors fit in this pipe analogy?
Semiconductors are like a pipe with a valve that can open or close depending on the temperature.
Okay.
At low temperatures, it's like the valve is mostly closed, so they act more like insulators.
Yeah.
But as the temperature rises, the valve opens up, allowing more electrons to flow, and they behave more like conductors.
So they're kind of in between, which I guess is why they're called semiconductors.
Right.
This is where silicon comes in, right?
Yes.
It's a superstar of the semiconductor world.
Precisely. Silicon is special because its conductivity can be carefully controlled by adding tiny amounts of impurities, a process called doping.
Doping.
Yeah, think of it like adding a pinch of salt to a recipe. It can drastically change the flavor.
So instead of changing the flavor, doping changes how well silicon conducts electricity.
Exactly. And the beauty of this is that we can fine-tune the conductivity to just the right level, which is crucial for building things like transistors and diodes, the building blocks of modern electronics.
Okay, doping sounds pretty powerful.
Yeah.
Can you give me an example of how it's used in real life?
Sure, imagine you're designing a computer chip. You need specific areas of the chip to have very specific conductivities to function as transistors.
Right.
By precisely doping the silicon in those areas, you can essentially engineer the electrical properties to create those transistors.
So it's like we're drawing circuits, but instead of ink, we're using atoms.
Yeah.
That's pretty wild. But this brings up a question. How do scientists figure out all those details about the charge carriers in a material?
Well, scientists use a clever technique called the Hall effect.
Okay.
Imagine you have a thin strip of material with a current flowing through it.
Okay.
Now apply a magnetic field perpendicular to that current. What happens is that the charge carriers, whether they're electrons or these holes that act like positive charges, get deflected by the magnetic field. This deflection creates a voltage across the material, and by measuring this voltage, we can figure out the type and concentration of the majority charge carriers.
That's amazing.
Oh.
So by using magnets, we can essentially interrogate the material and get it to spill its secrets about its charge carriers.
That's a great way to put it.
But let's get back to semiconductors for a moment.
Mhm.
You mentioned transistors and diodes as the building blocks of electronics. Can you explain a little more about how those work?
Absolutely. Let's start with diodes. You can think of a diode as a one-way valve for electrical current.
Okay.
It allows current to flow easily in one direction but blocks it in the other. This is possible because of something called a p-n junction.
A p-n junction, what's that?
It's basically a boundary between two types of semiconductors.
Yeah.
A p-type, which has an excess of those holes we talked about, and an n-type, which has an excess of electrons.
Uh-huh.
When you join these two types together, they create a region that acts as a barrier to current flow in one direction while allowing it to pass through in the other.
So it's like a border crossing, but for electrons and holes, that's pretty clever.
Yeah.
What about transistors? How do they work?
Transistors are like tiny amplifiers and switches. Think of it like this. A small current flowing through one part of the transistor can control a much larger current flowing between two other parts. This ability to control a large current with a small one is what makes transistors so powerful.
Okay, so they're like tiny electrical valves or switches that can be used to amplify signals or turn circuits on and off.
Precisely, and there are different types of transistors, like junction transistors and MOSFETs, each with its own unique structure and operating principle.
We've talked a lot about metals and semiconductors, but what about other types of materials like ceramics and polymers? Are they all just insulators?
Well, most polymers are indeed insulators, but there's a fascinating world of conducting polymers.
Oh.
These special polymers can be doped just like semiconductors to achieve conductivities rivaling those of metals.
Wait, so we could have flexible electronics made from polymers in the future?
Exactly. Conducting polymers have enormous potential in applications like flexible displays, rechargeable batteries, and even wearable sensors.
Wow. It seems like we've only just begun to explore the possibilities of these materials. But before we get too carried away, let's take a moment to shift gears and talk about another important class of materials: dielectrics. These are the unsung heroes of capacitors.
You've probably heard of capacitors, those little components that store electrical energy. Dielectrics are the key ingredient that makes them work so well.
So are dielectrics like tiny batteries?
Not quite. Batteries store energy chemically, while capacitors store energy electrostatically. Think of a capacitor as two conductive plates separated by a dielectric material.
Yeah.
When you apply a voltage across the plates, an electric field builds up, and the dielectric material becomes polarized.
Polarized, what does that mean?
Imagine the molecules in the dielectric material are like tiny compasses. When you apply an electric field, they try to align themselves with the field, creating regions of positive and negative charge within the material. This polarization actually enhances the capacitor's ability to store more charge.
So the dielectric material is helping the capacitor hold on to more energy.
Exactly. And the ability of a material to polarize is measured by something called the dielectric constant. The higher the dielectric constant, the better the material is at storing energy in a capacitor.
That makes sense. It's like having a bigger container to hold more water.
Yeah.
But you mentioned earlier that not all dielectric materials are created equal. What makes some better than others?
Well, the way a material polarizes depends on its structure and how its molecules respond to an electric field. Some materials have molecules that are already polar, meaning they have a positive and negative end, even without an applied field. These materials tend to have higher dielectric constants. Other materials can become polarized under an electric field due to the shifting of electrons or ions within their structure.
So there are different mechanisms at play, and they all contribute to the material's ability to store energy in a capacitor. That's pretty cool. But is there a limit to how much charge a capacitor can store?
Yes, there is. Just like a balloon can only be inflated so much before it bursts, a dielectric material can only withstand a certain electric field strength before it breaks down. This is called dielectric strength.
So if you try to cram too much charge into a capacitor, the dielectric material could fail.
That's right. And when a dielectric material fails, it can no longer function as an insulator, and the capacitor essentially becomes a short circuit.
Yikes. So choosing the right dielectric material with a high enough dielectric strength is crucial for building reliable capacitors.
Absolutely. You need to consider the operating voltage and the amount of energy you need to store when selecting a dielectric material.
Now, remember you mentioned some special cases, ferroelectrics and piezoelectrics.
Yeah.
What makes them so unique?
Ferroelectrics are like the rock stars of the dielectric world. They have a unique property called spontaneous polarization, meaning they're polarized even without an external electric field.
So they're always polarized no matter what. How is that even possible?
It's due to their crystal structure. The atoms in a ferroelectric material are arranged in a way that creates a permanent electric dipole within the material. And the amazing thing is you can actually change the direction of this polarization by applying an electric field.
So it's like a switch you can flip back and forth.
Exactly. This property makes ferroelectric materials ideal for use in memory devices.
So those tiny memory chips in our phones and computers might contain these ferroelectric materials?
They very well could. Ferroelectrics are also used in high-performance capacitors and sensors.
That's incredible. Now what about piezoelectrics? What's their superpower?
Piezoelectric materials are the masters of energy conversion. They can transform mechanical energy into electrical energy and vice versa.
So if you squeeze a piezoelectric material, it generates electricity.
Exactly. And conversely, if you apply a voltage to a piezoelectric material, it will physically deform.
Wow, that's amazing. Where do we see these materials in action?
You'll find piezoelectrics in all sorts of everyday devices. For instance, microphones use them to convert sound waves into electrical signals, and quartz watches use them to keep time. They're also used in ultrasound transducers for medical imaging and even in inkjet printers.
It's mind-boggling to think that these materials can do so much simply by changing shape or responding to an electric field. It makes me wonder about what other kinds of materials with unique electrical properties are out there waiting to be discovered.
It really is fascinating. We've only just scratched the surface of what's possible. Think about materials with properties like superconductivity, where electricity can flow with zero resistance.
Zero resistance. Wouldn't that revolutionize everything from power grids to computers? But I thought superconductivity only worked at extremely low temperatures.
That's true for conventional superconductors. But imagine if we could achieve superconductivity at room temperature. It would be a game changer.
It would be incredible. But it sounds like something out of science fiction.
Maybe not for long. Scientists are constantly exploring new materials and uncovering new phenomena. The field of materials science is constantly evolving.
It's exciting to think about what the future holds. We've covered a lot of ground today, from the basic concepts of conductivity and resistance to the fascinating world of semiconductors, dielectrics, and even the potential for room temperature superconductors.
And we've seen how these electrical properties of materials are not just theoretical concepts, but rather the foundation of the technologies that shape our modern world. From the transistors in our smartphones to the capacitors in our computers, from the microphones that capture our voices to the ultrasound machines that peer inside our bodies, the electrical properties of materials are constantly at work, making our lives easier, healthier, and more connected.
It's truly remarkable how the behavior of tiny particles like electrons can have such a profound impact on our lives.
It really highlights how interconnected science and technology are, and the best part is there's still so much more to discover.
Yeah,
New materials with even more amazing properties are waiting to be found.
right.
And those discoveries will undoubtedly lead to even more incredible technologies that we can't even imagine today.
Yeah, it really makes you appreciate the work that materials scientists do,
Absolutely.
constantly pushing the boundaries of what's possible.
Their work is fundamental to so many advancements, not just in electronics, but in fields like energy medicine and transportation.
You know what fascinates me is that we've been talking about materials that are already being used in all sorts of applications, but what about the future? What are some of the emerging areas in material science that have you excited?
Oh, there's so many. One area that I find particularly intriguing is the development of nanomaterials. These are materials that are engineered at the nanoscale, meaning they have dimensions of just a few atoms or molecules.
Nanoscale, that's incredibly tiny. How do you even work with something that small?
It requires specialized tools and techniques, but the potential payoffs are huge. At the nanoscale, materials can exhibit completely different properties than they do in bulk form. For example, you mentioned graphene earlier.
Right.
It's a single layer of carbon atoms arranged in a honeycomb lattice, and it's incredibly strong, lightweight, and an excellent conductor of both electricity and heat.
So we're talking about materials with almost superhero-like properties.
Exactly, and we're only just beginning to explore the possibilities of nanomaterials. They hold immense potential for creating more efficient solar cells, faster and more powerful computers, and even new types of sensors that can detect minute changes in the environment.
It sounds like the future of material science is going to be even more mind-blowing than what we've seen so far.
I think that's a safe bet, and it's not just about discovering new materials, but also about finding innovative ways to use existing ones. For example, 3D printing is opening up exciting possibilities for creating complex structures with tailored properties, and bio-inspired materials are mimicking nature's designs to achieve remarkable feats of strength, flexibility, and adaptability.
It's truly an exciting time to be following the world of materials.
It is, and I think it's important for everyone to have at least a basic understanding of how materials work, especially in a world where technology is advancing at such a rapid pace. The more we understand about the materials that make up our world, the better equipped we'll be to make informed decisions about their use and development.
I couldn't agree more. Well, dear listener, I think we've successfully completed our deep dive into the electrical properties of materials. We've explored the fundamentals of conductivity, delved into the fascinating world of semiconductors, and uncovered the secrets of dielectric materials. We've even touched upon the mind-boggling potential of nanomaterials and other emerging areas of materials science.
Hopefully, you've gained a new appreciation for the hidden world of materials, a world that's often taken for granted, but is nonetheless essential to our modern lives.
It's a world that's full of wonder, complexity, and endless possibilities, and who knows, maybe this deep dive will inspire you to explore further, to learn more, and maybe even contribute to the next generation of groundbreaking materials and technologies.
Remember, the future is literally made of the materials we discover and create.
So keep those electrons flowing, and until next time, happy exploring.